All right, so in this video, we're going to talk about functions of several variables. And so we're temporarily transitioning away from our vector valued functions, and we're going to be viewing them more in the traditional way. So we know from algebra that y equals f of x is the notation for a function. We know that the x is the independent variable, the y would be the dependent. And when it comes to domains, since x is the independent variable, then the domain that we talk about so much is always going to be us investigating the x coordinates. And I say x because, of course, we know we can use different letters in there, but it's always going to be investigating the independent variable for the domain. And many times we give domains an interval notation for functions set up like this. Now, we're going to branch out and say that z equals f of xy. So now z is a function of both x and y. X and y both are the independent variables. And therefore, when we talk about the domain, we've got both x and y as what we need to investigate when studying and figuring out what the domain is. Now we can carry this notation down as far as we want to go. Generally speaking, you're familiar with this notation: single variable, single independent variable, and then we've got our third dimension function here where we're studying a surface, z equals f of xy. And then if we wanted to carry it on, w equals f of xyz. And then again, you could keep going if you wanted to. We're not really interested much beyond that. But for the w being a function of x, y, and z, this would of course mean that x, y, and z are the independent variables. And when we talk about the domain of such function, we're going to be needing to investigate the x, y, z ordered triple. All right, so again, kind of just in summary, most of this is just notation, but this coming from algebra and having worked with domains before, we usually write these domains in interval notation. Now when we study the domains of these types of functions, we're going to be needing to look at xy ordered pairs that are allowed to be plugged in. Here, xyz ordered triples that are allowed to be plugged in. All right, so for the first example we're going to look at, we're going to take a look now at a function of x and y. This is considered to be a real valued function, and we are going to study the domain of this. We're going to figure out what the domain is. Now, because it has both x and y as independent variables, the domain is going to be the allowable xy ordered pairs. So we can't necessarily write that in interval notation, but one of the things that you've done in past courses, I know, is you've actually graphed solution sets. Now, the solution set that I'm talking about is the domain, but it all works hand in hand. So let's figure out what the allowable xy order pairs are going to be for this particular function. Well, we know that inside of a log, inside these parentheses, that quantity has to be positive. So xy has to be positive, which actually gives us two possibilities. X can be bigger than 0 and y could be bigger than 0, or x could be less than 0 and y could be less than 0. So if they're both positive, multiply them together, you get a positive. If they're both negative, multiply them together, you'll still get that positive inside the log. So now, to graph this, we'll go ahead and put together the xy plane. And that makes sense, right? Because we have the x and y being our independent variables, so we're going to graph the domain in the xy plane. So now, where do these points exist? They're going to exist where x is bigger 0 and y is bigger 0, so that looks to be right here. So let me go ahead and graph that in. And when x is less than 0, y is less than 0, that would be this quadrant here. So I'll sketch that in. So far what we're saying is that all ordered pairs in this quadrant and this quadrant, all xy ordered pairs, if you plug them in here, you'll get a z value coming out. Okay? So now, there's one other thing we have to take into consideration, and this is very easy to forget. Since these are strictly bigger or strictly less, we can't actually include values that would make x or y equal to 0. And those values would be along the x-axis and the y-axis. So I'd want to make sure I'm very, very clear to put a dashed line separating everything. If you remember back from algebra, the dashed line means don't actually include that boundary. Okay? If it was inclusive, it would be the solid line. Okay, so again, pretty straightforward stuff. We're just now having to accept that writing the domain or figuring out the domain is going to be a little bit different, but that's okay. Now, the last thing I want to point out, because this is very visual, is what does the graph of this actually look like? Well, I don't really know. But what I do know is that if our z-axis starts here, let's say, and goes up and down, and I guess the way they're looking at the screen, it would be coming out at you and then going back into the whatever's behind you. So to give it its third dimension, what it's saying is that this surface right here exists above, below, or in this region, above, below, or in this region. There actually won't be any graph vertically along the z-axis in these two regions here. All right, so for this one, we're actually taking it up a dimension. And so in us studying the domain of this, we're really going to be interested in the x, y, z ordered triples. Okay, so now when we sketch the actual domain of this function, we're actually going to be in R3. Okay, so let's take a look at what we're allowed to have and what we're not allowed to have. Being an inverse sine function, inside the parentheses here, we know has to be bounded between 1 and -1. So I'm actually going to set up an inequality. I'm going to say -1 less than equal 3 minus x squared minus y squared minus z squared less than equal 1. You've heard me say many times that the sine function is always bounded between 1 and -1. Therefore, for the inverse sine function, the inside here has to be bounded between 1 and -1. So now I'm going to manipulate these separately a little bit. So this first one here and then the second one would be here to get two separate inequalities. That's just going to be a little bit easier to look at, I feel. Certainly not required, but I do think it's easier to look at. So x squared plus y squared plus z squared less than equal 4. And x squared plus y squared plus z squared bigger equal 2. So what that means is we've got a sphere right here centered at 0, 0, 0, radius 2. Sphere centered at 0, 0, 0, radius square root of 2. So now when I graph this, and again I'm going to be in the x, y, z space. So I'll have my x-axis, my y-axis, and my z-axis. Here's the larger sphere right here. Let's kind of sketch this in. And then the smaller one might look something like this. And so if our sphere has to be less than equal 4, this sphere has to be greater than equal 2, looks like our domain for this thing right here is going to be all of the x, y, z ordered triples that lie between these two spheres. Okay, so again, domain is very visual. Graphically, it's easy to understand. When it comes to expanding into larger, higher dimensional things, it is definitely more of a intuitive idea of where you're going to be allowed to get your points, creating the dependent value. All right, so now we're ready to discuss contour maps and level curves. Now, as you can imagine, what you're seeing on the screen here would be very difficult to create by hand. And so a lot of this stuff will be already presented to you or could be created by a computer. So these are the functions that we were talking about a little while ago. So something to the effect of z equals f of xy. Here are our surfaces that we're talking about, all right? Now, if anybody has been out hiking or whatever and you've looked at a topography map, a lot of times you don't necessarily need all of this information because this information down here will tell you the same thing. These are called contour maps. And so the most obvious way to kind of think about this is almost signifying elevation. So for this first one, you can see that you very clearly have some peaks here. You've got some rippling. And then if you look down here, you can also see where you have these open circles here, here, here. Those would be where the peaks or the valleys might be. The closer together these lines are, means the steeper you're either going up or down. Similar over here, you can see these are very, very high and you go up and down very quickly. So there are your peaks. Maybe a valley down here, you can't really see, but probably a valley down there. And then these lines are really close together. Now, again, these are very, very helpful a lot of times because not always will you have access to the actual contour map. However, these level curves, these collection of level curves right here creating this contour map are somewhat easy to come up with. And so, depending on the context of the problem and what it is you're trying to do, one might be easier to come up with than the other, one might be completely unnecessary, but in short, they both kind of tell you the same thing. All right, so the level curves, we've actually done some of that when we talked about quadric surfaces. So by us looking at or taking one of the variables and letting it be a constant, that would then give us, take that surface and bring it down to a curve and putting all that stuff together, you'd have a collection of level curves. Now you can see we're up a dimension, and so when we scale it back by letting this guy be a constant, now we will be looking at a level surface. Okay, so this idea, this problem, what we're doing here is no different than what we've done before. Again, we're just up in a higher dimension now, creating a level surface. So all that I'm going to need to do is take the x, the y, and the z, plug it in here, and I'll find out that f of negative 1, 2, 1 is going to be the natural log of 1 plus 4 plus 1, which equals the natural log of 6. Therefore, the natural log of x squared plus y squared plus z squared is going to be equal to the natural log of 6. And you can see this is a level surface. It's going to be a level surface going through the point negative 1, 2, 1.